Okay, so here is a sample problem related to the delta G equations that we mentioned in the previous video. You are studying this reaction. This reaction shows up all the time. This stuff is ammonia, in case you care. It says the standard change in free energy for this reaction is negative 32.96 kilojoules per mole. Here we have the standard change in free energy. It is a negative number. That means the forward reaction is spontaneous under standard conditions. Those are the conditions that I mentioned in the previous video. First part of the question is, what is the equilibrium constant for the reaction when the temperature is 35 degrees Celsius? I tell you R. The second part of the question, which we will answer later, is you're performing this reaction at 35 degrees Celsius. The reaction reaches equilibrium. At equilibrium, the concentration of ammonia is a certain amount. Concentration of H2, so we know the concentration of this stuff, we know the concentration of this stuff. The question is, what's the concentration of this stuff under those conditions? The only way that we can answer this question is we have to be able to answer the first part. We have to be able to get the equilibrium constant. So let's get the equilibrium constant. Okay, so here's a repeat of the question from the previous slide. Here's the R number, which you can either look up or I would tell you. Here's the equation that we are going to need. The standard free energy, the question says it's this number, so we're going to replace this with this number here. That's going to go there. The R number, this thing here, is going to go in place of R. The temperature, there's the temperature, that's going to go here, but remember, we need to convert this to Kelvin. And the only thing that we won't know in this equation is the equilibrium constant, and that's what the question is asking. So I'm going to go through this step by step. In the first step, I'm replacing the symbol for the standard change in free energy with the actual number in this case, so there it is. In the second step, I replaced the R number. I replaced the symbol for R with the actual R number, with its units. There's the negative sign there. I also replaced the symbol for temperature with the actual temperature. Here's the actual temperature, and you can see I converted it to Kelvin. So 35 degrees Celsius is about 308.2 Kelvin. Now the only thing that we have left to do is get the equilibrium constant alone, which means we need to get it away from these things. Since they are all multiplied together, to get them away we have to divide. So we're going to divide this side by negative 8.314 times 10 to the negative 3 kilojoules per Kelvin per mole. And we're also going to have to divide the right side by 308.2 Kelvin. If we do that, the numbers will reduce away to 1 and the units will cancel. But we have to do this to the other side as well. So we're going to divide the left side by negative 8.314 times 10 to the negative 3 kilojoules per Kelvin per mole, and also divided by 308.2 Kelvin. So this right here is this part here, the left side of the equation, before I do the division out, but just so that you can see it more clearly because it's all smushed up over here. The one thing that I want to point out is you're dividing a negative by a negative, so those will turn into a positive. You have kilojoules in the numerator, you have kilojoules in the denominator, those will cancel. You have moles to the negative 1 in the numerator, moles to the negative 1 in the denominator, those will cancel. And then you're multiplying Kelvin to the negative 1 times Kelvin, those will also cancel. So all the units are gone on the left side. If you remember from the previous week, I said that equilibrium constant is usually written without units for reasons that we won't go into, so this hopefully makes sense that it has no units. If you do this division out, 32.96 kilojoules divided by 8.314 times 10 to the negative 3, also divided by 308.2, you get 12.9. So 12.9 is equal to the right side of this equation, which is the natural logarithm of the equilibrium constant. So we're almost there, right? The question says, what's the equilibrium constant? We've got that pesky natural logarithm that we need to get rid of, and the way that we get rid of natural logarithm, the inverse of the natural logarithm, is e to the whatever power. So if we raise both sides, we do e to both sides of the equation, then this natural logarithm will go away, and e will go away, and we'll just get k to q. So e to the 12.9 is going to equal our equilibrium constant. Remember, E is just a number. It's equal to about 2.718, something like that. And if you do this out on your calculator, if you do E to the 12.9, here's your equilibrium constant, 4 times 10 to the 5, which is, so it's a big number, right? KEQ for this reaction under these conditions, much bigger than 1. That means for this reaction up here, the right side is winning, and the right side is winning by an awful lot because this is way bigger than 1. So at least under these conditions, the reaction favors products. So that is the first part of answering the question. There was a second part. Here it is. You're studying this reaction, blah, blah, blah. You're performing the reaction at 35 degrees Celsius, which is where we figured out the equilibrium constant. Your reaction reaches equilibrium. The concentration of ammonia, this stuff is 8 molar. Concentration of hydrogen is 0.1 molar. What's the concentration of N2? Well, this is pretty straightforward. The formula for the equilibrium constant for this reaction is going to be the concentration of ammonia at equilibrium raised to the second power divided by the concentration of N2 at equilibrium raised to the first power, also divided by the concentration of H2 at equilibrium raised to the third power. That's the formula for the equilibrium constant for this reaction. But we know what this number is because we figured it out on the previous slide. We know that it's about 4 times 10 to the 5. So we can shove this 4 times 10 to the 5 into this equation, and I just did. We also know what the concentration of this is at equilibrium because they told us. We also know what the concentration of H2 is at equilibrium, so we know this number as well because they told us. The only thing that we don't know is the concentration of N2, and, well, I'm pretty sure that's what the question was asking. What's the concentration of N2? So again, this turns into algebra. What we have is 4 times 10 to the 5 equals this business here. So 8 molar is the concentration of the ammonia. We're going to have to square it. 0.1 molar is the concentration of H2. We're going to have to cube it. If we do 8 molar squared, well, 8 times 8 is 64. So we're going to get 64, and the units are going to be also squared. If we do 0.1 molar cubed, that turns out to be 0.001, and the units are also going to be cubed, so it's going to be molar cubed. This stuff here is the concentration of N2, and we don't know what it is. So here we have 4 times 10 to the 5 equals 64. I'm just going to keep the units out of this to make it a little less messy. Divided by x, also divided by 0.001. So we need to figure out what x is, we need to get it alone, and we need to get it out of the denominator. To get it out of the denominator, well, there's a bunch of things that we can do. The simple thing to do is we can pretend the left side is divided by 1, because that doesn't change anything, and then we can cross multiply. So if we cross multiply, we'll do 1 times 64. It's going to equal 64, is equal to 4 times 10 to the 5 times x times 0.001. So 4 times 10 to the 5 times x times 0.001. And to get the x alone, we have to divide both sides by 4 times 10 to the 5. And we also have to divide both sides by 0.001. And if you do it on the right side, those numbers will reduce away to 1. You'll have x all alone is equal to 64 divided by 4 times 10 to the 5, also divided by 0.001. And apparently, if you do this out, the concentration of N2 you'll come up with this number, 0.160 molar. So this is the concentration of N2 at equilibrium at 35 degrees Celsius if the concentrations of the other things are what they told you they are. So that's the answer. The other thing that I want to go over is the problem set. So here are 2 problems. First problem is related to the video that we did last week. Here's some reaction. Here are the concentrations of the reactants and the product at different times. And what does it want to know? It's to know the value of the equilibrium constant for this reaction under these conditions. So pretty easy if you follow the video that we did in the previous week. Here's another problem. It tells you, so this is figuring out the equilibrium constant of a composite reaction. So this is some pretend reaction, and this reaction is composed of these 2 little reactions. So this is also related to a video that we did last week. You're going to have to use these two little reactions to try to compose this reaction and then figure out the equilibrium constant. That's the end of the video. That's the end of the videos for the week. So have fun. Enjoy the heat. Responsibly, I guess. Bye-bye.
Well, it's all you kids out there that hate your mom and pop forcing you to eat everything that's on your dinner plate every night. Yeah, when I was a little kid, see, I never liked to eat. And Mama put things on my plate and I'd dump them on her feet. But then one day she made this soup, I ate it all in bed. I asked her what she put in it and, well, this is what she said. Oh, chicken lips and lizard hips and alligator